So are you going to introduce me?
So,
I'd like to introduce Ross Hoffman. He's been working at AER for a long time. He's an expert in ready to transfer, Aussie, and many other things. Right now, he's actually one of the collaborators for the for SID's team in the AI at the University of Maryland. And Ross has worked on this particular progress in forecast skill, comparing with NWP multiple centers. So he's going to talk about the progress in forecast skill, comparing NWP centers, NSET, European Center, and UK Met.
Okay, hi everyone. So I'm really glad to visit. Although I'm an employee, I spend most of my working days in my home office in Cambridge, Mass. I did work at Goddard Space Flight Center as a postdoc with Yumi Yakame. I met her at MIT, where I did my graduate work. And after that, I joined AER for many years. And since 5 years ago, I've worked with Bob Atlas on Aussies mostly. And not only Bob Atlas, but Sid Bukabara and several other people in that project. And with Bob retiring, I decided, I asked Sid if he could find a home for me up here, and he did, so thank you. So I'd also like to say, I had a cold just recently. I'm still getting over it. If I have a coughing fit, I will recover. Don't worry. Try to hydrate. So how did we get started? We got started because sometimes you're faced with this kind of scorecard where there's many, many different verification metrics. How do you make sense of it all? So, and originally, oh, thank you. Originally, our project started because Sid's group had done a data gap OSE impact experiment, and they wanted to come up with a single number for each experiment that gave a sense of how skillful that experimental configuration was. So to collapse everything, they used a method to normalize each score and then combine all the scores. And this is the basis of what I'm going to show you here. Let me go back to the beginning. I don't have control of the screen. Okay, thank you. Okay, so there are many co-authors on this work. These are the co-authors that worked on the most recent paper that I'm mostly presenting today. And we're from all different places, and you can see I'm from many of those places. So here's the introduction to the study. We looked at deterministic forecasts for 3 leading NWP centers, UKMO, NSET, and ECMWF. And this shows the flow chart for how we created what we call summary assessment metrics. It's a way to combine all your metrics into one number. And so we're using these terms PAMs, NAMs, and SAMs. So primary assessment metrics are what we get from, say, the VSDB data set when we calculate anomaly correlations or root mean squared errors. And for each of those, we use, in this particular type of normalization, we use a reference sample to normalize each individual PAM to create a NAM, a normalized assessment metric, and then we sum them, or actually we average them to create a single summary assessment metric. So the idea is for any individual metric, you convert to a number between 0 and 1, 0 being horrible, 1 being the best. And that's the kind of normalization we're looking for. Since for any distribution, if you invert the cumulative density function, you get the probability, and probabilities for any distribution are uniform on 0 to 1. So this is an ideal way to convert from any number to a number on 0 to 1. You just use the distribution of the numbers, and you get a number between 0 and 1. And under the null hypothesis that there is no impact of what you're doing on the forecast, that all the forecasts are basically the same, then that uniform distribution will the expected value will be a half, and the variance will be 1/12. And when you average many of them together, you'll still have a half for the expected value, and the variance will be quite small, because it'll be 1/12 divided by n, the number of things you're averaging over. Of course, we have to take care of correlation, so it's not quite like that. And when we average many things, central limit theorem applies, and it turns out, in fact, that we don't need to use a sophisticated normalization. Any normalization will actually work. So the initial experiments, the initial use of this idea, use the minimum and maximum of the reference sample to scale all the data. So that's really a linear mapping of each RMSE or each anomaly correlation to 0 to 1 by using the minimum and maximum. In this work, we're using mostly the empirical cumulative density function to do the mapping from 0 to 1. But as long as we rescale things so that they have the same expected mean and expected variance, when you sum over many things, average over many things, you get the same results. And I'll be showing results for two very different normalizations as we go through this. So during these 3 years, here are the upgrades that I know about that I was able to find. And I'll come back to this chart several times as we go along. But for sure, people in this room will recognize the three upgrades that happened at NCEP, and the most important and interesting one was the upgrade to the 4D N bar. For context, I'm just looking at 3 years. It's just the end of this chart. But this shows 2 decades, from 1998 to 2018, from the WMO website where they collect these statistics, of the evolution of not anomaly correlation at 500 millibars, but root mean squared error at 500 millibars. And you can see really good declines over the, 2 decades ago. We made lots of progress, all the centers did. Different colors are different centers, and there was some change in how they manipulated, how they processed the data that went from the solid lines to the dashed lines. But just look here, towards the end of the period, everything's kind of really flat, and these have been averaged with a 1-year moving average. ECMWF, the red dashed line, is still improving a little bit. The other centers don't seem to be improving. For this one metric alone is not so important, of course. So I'm going to use this as an example to show the procedure of going from PAMs to NAMs to SAMs. So this is the wind root mean squared error in meters per second for just one time period, a 5-day forecast, and just one level, 500 millibars, and just for the northern hemisphere. And you can see there's results for the 3 centers. They're different colors are used for each center, and there's 2 sets of curves. In one I've applied a monthly moving average, and the other I've applied an annual moving average. So this is a metric where there's a great deal of variance. It's the northern hemisphere winds where the jet stream changes a lot from season to season, the overall. So there's a big seasonal signal here. When you average it over the year, you can see things are improving a little bit. The RMSE is decreasing a little bit.
Is
Yes.
Northern Hemisphere 20 to 80 north?
20 to 80 north, yes. Yeah, I'm using the standard BSDB data sets to create all the statistics I'm showing here. Excuse me. So what else can we see? So we can see that ECMWF is like 0.5 meter per second in RMSE error, better than the other 2 centers. It's hard to choose between the other 2 for this one metric. But of course there's many metrics, and I started off showing you this. This is ECMWF scorecard for the upgrade from IFS cycle 45R1 from 43R3. So this is a very recent upgrade. It's in one of their recent ECMWF newsletter publications. And you can see there's a lot of complexity in this. And if you study it hard, you'll figure out things that are going I'm just going to blow up the part that's enclosed in the black box. So this is just the part for the high-res forecast, the deterministic forecast, and compared to analysis only, not compared to observations. And you can see there's improvements most everywhere, but not the lower level temperatures so much. But this is one of the problems we all face. How to validate and convince yourself that it makes sense to start using a version operationally. Look at all these scores. I mean, if you're only interested in low-level temperatures, you wouldn't make this upgrade. But in fact, they do make this upgrade. Yes, yes.
Well, these are highly correlated with each other. The 150 millibar height and the 100 millibar height are going to have similar results on this. And
Yes.
so the other. So you really only have a few scores here in reality.
No, there's many scores. There are some correlations there. And I can talk about that more later. But we did look into correcting our work for correlations. And in this, they do account for serial correlations. They don't look at anything else. Okay, enough about that. But how do we combine such a thing? So this is the picture I showed before. So, or in many cases, we just focus on a few key primary assessment metrics: 500 millibar height, 250 RMSE winds. But there's many other aspects of forecast skill, and we are creating the metrics, but it's hard to use all those metrics to present to management to make a decision. So for the work I'm going to show here, these are the assessment metrics I started with. So there's 7 different dimensions of this giant array of metrics, and the first dimension is forecast time from 1 day to 7 days, 5 different levels in the vertical, 3 domains, 20 degrees north and south being the dividing line, 3 variables, height, temperature, wind, anomaly correlation, root mean squared error, and absolute mean error. And anomaly correlation is calculated from VSDB, so it's only available for certain levels for certain variables. Yes, you have a question?
So these are against their own analyses.
I'm sorry?
Each center is against its own analysis.
Yes, it's
Yeah.
what has been collected here.
And you don't have anything against observations. I mean,
No.
really.
No, but, that's one reason why I'm not using the 0 forecast time. It would be senseless. Verified against itself. And so it's every 0Z forecast for the whole 3 years for those 3 centers. Now, there's different ways you can define the reference sample, and I've explored several of them. So the first way I'm going to call all, where I use every day during the 3 years and all 3 centers. I put them all together, and I use that to define the probability distribution for each of the metrics. Another way is to do each center by itself, where we just use all 3 years of a particular metric for a particular center to calculate to do the normalization for that center. So I'm going to start off by showing you results for all, where we're intercomparing the centers. But later I'll show results center by center only. Well, I'll show all 3 centers at once, but they'll only be validated compared to their own skill during the 3-year period. So these are some examples of the cumulative density functions. Again, for that same particular metric that I showed before, RMSE of 250 millibar vector wind in the northern hemisphere. And for each forecast time, there's a different probability distribution and a different curve. The dark solid, the heavy solid curves are using the all definition of the reference sample. So all 3 models, all 3 years, for every day during 3 years. And you can see how, of course, wind RMSE increases as forecast time increases. So, it goes from 24 hours on the left to 168 hours on the right. But then if we looked at just ECMWF compared to itself, those cumulative density functions are slightly different, and those are the light solid curves. And if we look at just the values for January, we get the dash curves. So depending on the reference sample, you have a different distribution, you will get a different answer. This looks into this a little further, showing for just the 5-day RMSE error, the probability distributions for the different months. So it goes from the right, the largest errors are in January, then February, and through the cycle of the year, the smallest errors are in, for months 7 and 8, July and August. So once we have one of these curves, this shows how to, take values for a particular forecast metric, for a particular PAM, and convert it to a NAM. So this is from one of the earlier papers where we were looking at the OSE impact study that was done here. And you can see that 2-polar, 3-polar, and control are ordered that way because there's more data going into control than 3-polar is a data gap experiment and 2-polar is a more severe one. So this shows, so to map a particular metric to its normalized metric, you just take the value, go up to the curve, the cumulative density function curve, and go across, read across. We don't, of course, do that. It's more efficient to use the rank function to convert all the PAMs into NAMs pretty quickly and easily. So I won't say a lot about this, but the picture shows that there's 3 different ways. When you rank things, when you calculate the rank of a vector, if there's duplicates or triplicates, you have to decide the ranking. So one way of ranking things is like when you watch golf on TV, there could be 2 people in first. Then the second place person is really the third one. So there's different ways of ranking, and we use the average rank minus a half gives the right way to define the NAM, and this is defined in the appendix to the paper we published. The other normalizations are just a linear scaling. So this converts the picture that I showed before of the 5-day 500 millibar northern hemisphere vector wind RMSE from PAMs to NAMs. So the picture's basically flipped because errors, we've gone from errors to a kind of skill score where 1 is best and 0 is worst. But otherwise, it's very similar. We see the same seasonal cycle, we see the same improvement of ECMWF by a regular amount over time, and there's a slight improvement over the 3-year period. This is doing the same thing, but considering each center only with respect to itself. So now everything kind of lines up pretty well. It's hard to see any difference at all. One last one where we looked at things by month, that is all of the Januaries for all the centers were used to normalize all the January data. All the Februaries for all the centers were used to normalize all the Februaries, and that basically wipes out the annual cycle in this metric. So this shows the histograms for all the NAMs for 3 different ways of doing the normalization. So the first one is the empirical cumulative density function normalization. You get a very nice uniform distribution overall because we put everything together here. But you can see that the greenish blue color is ECMWF. It has more, its distribution is more skewed towards the better forecast. And the middle panel shows the results for using a min-max normalization, and the right-hand panel stretches out the min-max normalization to have the same mean and variance as the first panel A, and I call that rescaled min-max. And in what follows, I will show results both from using the normalization represented by A and the normalization represented by C, and the results are very much the same. So the exact way you do the normalization doesn't actually matter that much. So the left-hand side shows the SAM, the average of all the NAMs for the three centers. And the differences are rather small, really. I've changed the scaling on this panel relative to most of the others. It goes from 0.4 to 0.6 on the right-hand side, and most of the others it goes from 1/4 to 3/4. But we can see that ECMWF is best, NCEP and UK office are similar, but NCEP is doing better. There's a light gray band in the middle, that's a 95% confidence interval under the null hypothesis, and there's little error bars at the ends of these color bars, showing the uncertainty in each one. The color bars are using the ECMWF, the empirical cumulative density function normalization. The black outlines are using the rescaled normalization. They're almost the same, there's slight differences. On the right-hand side shows the variation from year to year. You can see each of the three centers is improving its summary skill score from year to year. We like that, we expected that. But we can also divvy this data up in different ways to get more insight into what's causing, well, more insight into the differences in the errors for the different models. So this shows how the error, or how the skill varies by forecast time from 1 to 7 days. And on the right-hand side, it shows it also for 1 to 7 days, but broken down by year. So we can divide up our overall data set, average over those sort of subdivisions, and get a sense of how the overall error varies in these different dimensions. So I'll just pick out one curve here. It's the purple curve with the solid filled boxes on the right. That's NCEP for 2017. And you can see that from 72 hours on, it's kind of equilibrated to one constant value. But the relative skill for that forecast model for that year doesn't vary very much from 72 hours out to 7 days. But at the beginning, it's much better at the beginning at 24 and 48 hours, and then it decays. I'll talk about this more later, but my feeling is this is related to improved initial conditions, because the main impact is at the initial time. We can also look at, of course, the different variables, the different domains. So look at different variables on the left. You can see UKMO is the worst for temperature, but NCEP is the worst for geopotential height. I don't have an explanation for that, but it jumps out when you look at the statistics this way. And if we look at the different domains, we can see UKMO is really pretty poor compared to the others in the tropics, and more equivalent to NCEP in the extratropics. This repeats the last figure for the different domains. And on the right side, further subdivides it by forecast time. And again, if you look at the purple filled squares, you see there's this really impressive decay in the skill of NCEP in the tropics, or you could put it the other way. NCEP is way more skillful at the initial time in the tropics than, for example, the other two centers. I'm not sure why. That's interesting. Wait, did I go my way? Oh, and this is by level and looking at different statistics. So you can see ECMWF is particularly good in the lower levels of the atmosphere. And in terms of the different statistics, it's interesting that UKMO is worse for RMSE errors, and not so bad for anomaly correlation. And yet, we know that UKMO uses a kind of summary assessment metric they call, I can't remember what they call it, but they do something in terms of RMSEs. So they're really tuning their model to improve the RMSE scores, and yet they're doing better anomaly correlation relative to the other models. So now I'm going to switch to this other normalization where we're comparing each center only to its own probability density function for the 3 years. So this shows year by year for the 3 centers, and when we compare each center to itself, we see a relatively similar improvement year over year. And the right-hand side shows that 2017, the solid-filled squares, all the centers have improved in. And we still see this interesting shape of the curve for INSEP that, again, I think indicates improved initial commits. So this is the chart I showed at the beginning. I'm now going to show the daily march of the summary assessment metrics. So for each day in the 3 years, we summed up all the available skill scores, normalized skill scores, average them, and we get the curves that I'm going to show. And first I'm going to show ECMWF, and these are the 4 upgrades. They have a regular march of upgrades, and any one of them doesn't seem to be a huge impact, but the last one, going to 43R3, was the biggest impact. The right-hand column shows the improvement in the summary assessment metrics in terms of percent. So it improved 0.05 before and after the upgrade to cycle 43R3. So this is what it looks like day by day. There's a lot of variability day by day in forecast skill. No surprise, even when we average over all metrics for that day, there's still a lot of, it looks noisy. The light gray shading shows the 95% confidence interval. You know, it's hard to say that there's, from looking at this, that there's a statistically significant trend, although, you know, when you look at the whole picture, you can see things are improving over time for ECMWF. Now I'll look at INSEP. There were these 3 upgrades. The 40 NVAR is the most important one. The first one actually shows a negative increase, but there were only 14 days in our data sample at the beginning of the cycle to measure it against, so it's really not important. So here's the INSEP trace of skill day by day. And again, number 2 shows the day when the 40 NVAR was implemented, and for sure there's a significant step. You can see that by eye. And again, now I'll show for UKMO, there were just 2 upgrades during this period, and the improvement in resolution, the PS39, is not so, didn't give much of an impact, but the improvement in the way they handled satellite observations in November of 2016 did give them a big step. We can kind of see it here. It looks like the step up occurred a couple of months before the actual implementation, but at first I thought, oh, maybe we're collecting the pre-operational test data, but I think it's just the way these statistics are. They're very variable. And there's a big change in how well all the forecast models do from month to month. There's a big improvement in skill, I'll show it in a moment, from summer into fall.
So,
Yes?
can you link these kinds of things to some of the physical cycles that are going on?
It's hard to. Well, I don't have, I mean, there's so many things going on besides the model changing. There's, of course, as you said, the synoptic conditions are changing. We didn't look at that, but it could be, we could stratify things by El Nino index or some other thing.
Yes, okay.
This is just averaging the 3 together and kind of blah. But when we take each one and average it on a monthly or annual with an annual moving average, we can start kind of see some comparisons. So they're all improving on the annual average. The shapes of the curves are a little different. I don't know what to make of that. And then there's definitely, they're in more or less lockstep when you look at the monthly averages from year to year. Not perfect, or else that average curve I showed 2 slides ago would look a lot more interesting. But when you look at these, for example, in the summer to fall transition in 2017, all of them had great improvements in forecast skill relative to themselves. This shows the average over the 3 years, month by month, and you can see it. As I mentioned before, the real improvement in overall forecast skill from July to the fall. So this is the first part of my talk. I'm going to summarize it. Then I have a few more other things, or we could just have a discussion. So clearly, all 3 centers improve over the 3 years. NCEP improves more at short-term forecast skill than at long-term forecast skill. And I would associate that with improving initial conditions. And certainly the 4D INVAR had a lot to do with improving initial conditions. The summary assessment metrics show that overall ECMWF is somewhat better than NCEP, which is better but only by a little bit compared to UKMO. Excuse me. But compared to the 20 years, when we look back at 20 years, the improvements that we're seeing in these 3 years are really small. And it's hard to detect at all. But by combining everything, we improve the signal-to-noise ratio. And for sure, the improvements at key upgrade times seem to be significant. So, to conclude, if we just focus on a few key PAMs, we could be confused because of statistical variations, statistically insignificant variations. So it's important to try to look at everything. And even what we looked at is not everything. Of course, we just looked at deterministic forecast skill scores. We should look at ensembles and other things. There's sure room for improvement. ECMWF is doing better. And it's clear that some of the improvements in operational systems have clear benefits. So it might be interesting to look at other centers, to look at things like relative humidity and precipitation, where there's more room for improvement. There's not that much room for improvement in the global model for the variables that we looked at. So, any questions on this part? Yes.
Okay. You may have said that, and I may have missed it, but I was wondering, why is the skill for several of the models increasing with forecast?
I'm sorry, I can't quite hear.
For several of the centers, it seems like the skill is increasing with forecast time. Or I may have misinterpreted the plot.
Well,
Or is that
each
something
forecast
normal?
time, in this way of looking at things, when we look at the 6-day forecast, we're only comparing things to other 6-day forecasts. So
Thanks.
it's not that. Any other questions? Yes.
So the fact that the short-range forecast at NCEP improves more than the other centers sort of reinforces the question whether we should be looking at the...
I'm sorry, I'm a little deaf. Could you speak a little louder?
So the improvement of NCEP at the short range
Yeah.
is validated here against the analysis.
Yes.
So this
Yeah,
reinforces
it was
the
also-
question whether we should be doing the verification against ARMS and comment on the assumption of observational
For
error
sure,
in
we
the
should
data
do that.
simulation.
And we could, be nice to have a consensus analysis to use instead of just use each center
Yeah,
against
but
each.
that's still
That's still biased.
Excuse me?
That's still biased. You want to use real
Observations?
observations. Yes.
But that doesn't give you uniform coverage.
Still
You're
give
damned
you
if
the
you do,
correct
and you're
skill.
damned if you don't, I'd say.
That'll still give you the correct skill. The first 24 to 48 hours,
There's only so much we can do with observation. Don't have observation with the southern hemisphere over like
well, the northern hemisphere has
Northern
plenty.
hemisphere also limited, constantly the US, there's not much observation with the mountain.
You have the
region.
US, you have Europe, and you have Asia. You have three big centers.
I guess the Ross is the double sort of. You get something.
For sure that you're making good points. We didn't do
I mean,
that.
you're not getting the
And-
real
And the
skill.
same kind of approach could be applied to other databases of errors.
Especially for,
So I have a detective story to tell you about. We started off actually doing this study with 5 different centers. We had, this was everything that Krish could find here on the databases at EMC. So we had Canadians, we had the Navy as well. We also had the JMA, Japanese Met Agency, but we only had forecast out to 72 hours, so we skipped that one. So here's the thing. In the, we just couldn't make sense of the Navy results. And so we decided we got to drop that at least. And then we thought, well, might as well just do the 3 best centers. Makes the paper more readable, simpler, but I still wanted to find out why the results from the Navy was so odd. And this will ring a lot of bells for all of you, I'm sure. So this shows, I've changed the colors, I'm sorry, the color scales. The colors that I'm using for the centers are shown in the legend. But the Canadian overall skill is worse than the 3 main centers, and the Navy is even worse than that. So this is using that kind of valid reference sample that include all the centers, so we're comparing them to each other in this particular plot. But now I'm going to switch to using each center by itself as the reference sample. So we're just comparing the Navy to other Navy forecasts. And there's something that stands out here. The left side shows year by year. So in 2015, the Navy was much better than it was in 2017, whereas all the other centers are improving over the 3-year period. What the heck is going on here? I'm looking for answers here. I don't see any.
EMC
The right side shows the same thing,
switch to different system.
by forecasting.
Russian medals.
So the triangles are 2017, and the triangles for the Navy are at the bottom part of the plot, and the circles, which are the 2015 for the Navy, are at the top. This is, again, comparing Navy only to itself. So I tried dividing up the data all different ways. I'm not going to bore you with all the different ways, but I'll show you this way. Oops. Oh, sorry. So this shows the day-by-day variation. But this is the way that helped me to understand what was going on. When I look at winds at 1,000 millibar, all the centers, including the Navy, are improving year by year. When I look at the winds above 1,000 millibars, no, the Navy is not getting better. Okay, so that's another hint. Anybody know what happened? It's not clear. I had many ideas. I thought, the Navy is only interested in wind at 1,000 millibars because that's where their ships operate. So they're, somehow or other that's getting into how they're improving their model. But no, that's not it. So we had a lot of help from some of the people at the Navy. I got in contact with Nancy Baker, and she asked some of the people working there to help us. And we found out that just in the middle of the period, in the middle of the second year, NavGem grids that were shared with NCEP changed from 1 degree to half degree. The filtering did not change. They use a Shapiro filter, which depends on the number of grid points. So when you use 1 degree versus half degree in your filtering, you're making a real difference in the filter in terms of what the spectral response is. So the half degree grids had a lot more small scales, a lot more. Those are the hardest things to predict. We all know this. The more small scales you leave in before you do your verification, the worse you're going to do. And so the Navy made that change right in the middle of our second year. So things got worse. The only question is, how come the 1,000 millibar fields didn't? Well, it turns out they don't filter the 1,000 millibar fields. So the filtering did not change, and improved. I mean, in fact, their model system improved over these 3 years. It's just we can't see it with the data sets that we've got. So Liz Satterfield, who I think was at University of Maryland when she started her graduate work, and Randy Paul at FN Mock helped us figure this out. I mean, that's the kind of thing that happens all the time when you do verification. I don't have to tell this group, right? If you smooth things out, you get better scores. So let's smooth things out a real lot before we do our verification. I have a couple more things to say. You got time?
Good.
Okay. So we also applied this to our OSE and OSSE work. And in particular, we had a series of, OSSEs are observing system simulation experiments. I hope you all have heard that before. But they're both impact studies. The OSSEs are done all in simulation, and that allows us to look at the impact of a new system that doesn't even exist yet. So ideally, the OSSE system is built of a number of components I'll show you in a second, and all of them should be realistic. The experiments we did were preliminary, simplified, and in particular we used low-resolution experimental, suitable for experiment version of the GDAS and GFS, and we didn't add observation errars to our simulated observations, which many would say, oh no, that's no good at all, but we'll see. So this is the flow chart for an OSSE. You start with a nature run. That's a long forecast. In our case, it was the G5NR that NASA produced, a 2-year, very high resolution, 7-kilometer forecast with many interesting aspects to it. And from that, we simulate observations, and we use it for calibration and verification. But the data simulation system and the forecast system is as close to operational as we could afford, which was the T670 forecast model using the T254 assimilation system. So OSSEs have been used for a long time for many purposes. I list a few here. So this is the experimental setup for these experiments. We did an OSSE using all the satellite data, an OSSE and an OSE, retaining only three of the satellite platforms in polar orbits, early morning, mid-morning, and afternoon. And then a 2-polar system where we X'd out the afternoon polar orbiter. And let's see, there's some details of these experiments. So before we apply an OSSE system to a new system, we want to check if the results for a data impact experiment correspond to what happens in reality. If not, we have to calibrate our results. And there's a few things you can do. One thing that's often done is to make the observation errors bigger or smaller so you get the right analysis differences. You could change some of the parameterizations in the forecast model, make the forecast model a little worse, because in the real world, the difference between the forecast model and nature is substantial. And we used another model, different model from NASA to create nature, but both being models, they tend to be more similar than any model in nature. So sometimes we change the forecast model we use a little bit to make it worse. Or you can adjust the results after the fact. So it turns out in our experiments where we are simulating quote, perfect observations without adding extra errors, the OSSE primary assessment metric analysis would show you it's too optimistic. Both the control experiment and the two data gap experiments gave you very optimistic results compared to what happened in the real data observing system experiment. But in terms of these summary assessment metrics where we normalize things, everything becomes much more comparable. So this shows a couple of the primary assessment metrics, 500 millibar high anomaly correlation, 250 tropics wind RMSE, and you probably can't see the details, but the the 3 experiments corresponding to the OSSI are all much better, higher anomaly correlation, lower RMSEs compared to what happened in the real-world experiments. But when we look at summary assessment metrics, I've matched these up. So the orange and gold are the control OSSE and the control OSE. And overall, we put all these together, we compared all these experiments to each other. I'm sorry, I said that wrong. We compared all the OSSE experiments to each other and all the OSE experiments to each other. And by doing that, the changes due to the data gaps are in a relative sense very similar. So there's a very good correspondence from OSSE to OSSE, from simulation to reality, when you look at things that are scaled and normalized. And this makes perfect sense, really. And you should divide things up by different levels. You can again see the same kind of correspondence. And there's a paper and an AMS presentation that describes this work. So that's it. Thank you. Any questions? Chris, yes. Right.
No.
You're a co-author. You can answer
No,
all questions.
I was just wondering about, I understand from this approach we can understand the data assimilation changes and the forecast improvements from center to center. But within a center like EMC, and if we are improving, let's say, the physical parameterization, land surface, so if we can really take some of those parameters or diagnostics from those kind of things and then create a SAM.
Well, if you run a parallel system, yes, you can do this. You can even use this to sort of monitor how the system's working this year. You could use, say, right now we're in 2019. We could use all of 2018 from the INSET system, from the EMC system, as the reference sample, and calculate these scores day by day. Everything will be referenced to 2018, but you could do it day by day and just update these charts as you go along.
For this upcoming implementation, we have run almost 4 years worth of retrospective experiments. We have all the base DB database saved. I think to answer earlier next rules question, we also have the verification against observation near the surface, at least over the Congress region. Is that possible? You run through your package and generate a SAM stance?
For sure, that's a good use of it. I mean, but I think it's important to define how you want to do the validation before you start doing the calculations, because you can always choose some things, cherry pick things. Or if you're interested in trying to discover where the changes had the most impact, it's fair to just use it as an exploratory tool. Depends, if you're going to make a decision, you need to set the goal ahead of time.
Put it another way, we have a VSDB for many regions and a lot more variables than what included in this study. What's preventing you from using all of them? Is computational or because
No, by all means, use all of them.
If we chose actually some of the most prevalent ones, we could have chosen everything. All the available variables.
One of the things you have to understand is a lot of our implementations also have data assimilation changes, and this does not monitor the data assimilation changes, whether they're good or bad. Only observations can do that.
You would have to look at
Right,
observations
exactly.
minus analysis at time
Right,
zero.
and Fang Lin, what he says is that those are available on the database right now, the comparison with observations as well.
I guess what the package, I understand, because they use it basically is pushing up data from our
That's right.
package. For our verification, like against the surface, we have the VSTP database set up that, but it can be used for the filter ops. And probably they have to think how to use those verification stats. It's not that easy, it can be merged into the system.
At least for the first 48 hours.
Okay, well, I'll say, I did the software development in R on my Macintosh. And, I converted the VSDB database into a NetCDF file. But, to implement it in some other system, there's only one line of code, really. I mean, it's all just keeping track of things. The calculations are really nominal. And even if you use a simpler normalization, just the min and max over the sample, it could be fine.
So all this normalization tools,
Pardon?
all your normalization procedure comes from the R statistical package?
Yeah, but I'm just using it to manipulate data. The only calculation is the rank of the data values.
So,
Oh, yeah. Jordan first, and then you.
Well, I have two things. One is, I guess, in terms of looking at how centers make their changes over time and analyzing that, and in support of looking right at the observations. All these improvements are part of the climatology of the analysis system, and some can take very long time to filter in, such that your verification of these analysis will be subject to these big changes from it. For example, if you change something in the soil moisture, it might take years for it to filter through in a permanent way to improve the analysis system, 12 months anyway. But some things are short, some things are long, and depending upon the analysis system itself without that.
Okay.
The other thing is that, I was going to ask you to put you on the spot, but I'll do it for you. For a long time in this period, the UK Met Office was deemed to be putting us into third place, and great decisions were made based on that. And here, it doesn't look like that anymore, and those decisions might, at least that component of them, were probably not true. And so, as you said at the beginning of your talk, budgeteers and administrators, management, makes their decisions based on their emotion, and this won't change it at all.
Well, as we saw, if you looked at anomaly correlations, you got one answer. If you looked at RMSEs, you got another answer.
Yes, so I was going to put you on the spot. Rate it for us, which is right. I don't know what you can.
It depends if the centers are smoothing their fields out, then they'll get better scores. You don't know what they're doing.
Yeah.
They may be
Yeah, or if
applying.
they have a big Shapiro filter.
That's
That
exactly
makes
my
sense too.
point, and it's possible that the ECMWF and us, or we are doing more filtering than the UK Met Office. I know that the UK Met Office forecasts are much noisier, have more energetics in them, and therefore they come down. But in anomaly correlation, they beat us.
Okay, well, these are all
One
good
final
points that
observation.
need to be considered whenever you're doing these kind of comparisons. I agree. Yes, you had a question.
So this seems to be a convenient way of combining a number of metrics into
Yeah, a
a
summary.
summary to end up with one number, and you can then use that one number to make decisions. However, it's also highly derived from a lot of different things, and it seems to be very difficult tracing back if you actually see an improvement. Why is there an improvement? Or if there is a degradation, why is there a degradation? Do you have any comments on how to address any of
It's
that?
definitely true that when you have made some changes and you look for whether the impact is positive or negative, it's very hard to figure out, especially these days as we're getting so closer and closer to maybe the best we can do with global models. So it's not an easy question. There's tracing things back is very, very difficult on a case-by-case basis. It's worth doing, and a skilled synoptician can sometimes explain that, okay, quality control eliminated this this observation in this case and not in the other case, and that led to a tiny change in the thickness, and as a result, we got a forecast dropout in the one case or the other. But it's not really satisfactory, even when you can track it down in one case. And in my experience, when you do impact studies and you try to track it down to what actually happened, you generally get frustrated. The impacts at 5 days, which can be rather large, can track down to like things that seem totally insignificant at analysis time. It's not an easy thing. Okay, anything else? Thank you all. Thank you for taking care of it.
So I would like artificial intelligence to tell me which metrics to choose that will support my decisions. That's really
I hear you.
Make your decision.
You got metrics, sorry. I've always thought it was very dangerous to rolled up
And then pushing for him.
metrics. Because, like you said, the Navy was